While tech school is not always a requirement for obtaining an electrical contractor's license, it offers structured learning, hands-on experience, and covers core electrical knowledge necessary for the exam. It can also help meet continuing education requirements for license renewal. To effectively prepare for the electrical contractor's exam, consider the following steps. Firstly, familiarize yourself with the exam structure and topics covered. Secondly, dedicate several hours per week to studying, using a study schedule or planner to stay on track. Thirdly, review the National Electrical Code, known as the NEC, and core electrical topics like electrical theory, wiring methods, electrical safety, and code requirements. Fourthly, solve practice questions regularly to test your understanding and identify areas needing more review. Fifthly, seek guidance from former electrical contractors, online forums, or tutors if you encounter difficulties. Recommended books for studying include the National Electrical Code, Electrical Contractors Exam Preparation by David Hayes, and the Electrical Contractor Licensing Exam Study Guide by Thomas Shoemaker. Online resources such as Electrician Exam Prep, COM Electrical Exam, COM, and Kaplan Electrical Contractor Licensing Exam Preparation course can also be valuable. When studying electrical theory, focus on understanding the fundamental principles that govern electrical circuits and systems. Key topics include Ohm's law, which states that voltage equals current times resistance, expressed as voltage equals current x resistance. Understanding this relationship is crucial for analyzing circuits and solving problems. Series circuits are characterized by a single path for current flow, meaning the same current flows through each component. The total resistance in a series circuit is the sum of individual resistances. Resistance total equals resistance 1 plus resistance 2 plus resistance 3, and so on. The voltage drops across each resistor in a series circuit add up to the total voltage supplied by the source. Parallel circuits, on the other hand, provide multiple paths for current to flow. The voltage across each branch in a parallel circuit is the same. The total current in a parallel circuit is the sum of the currents in each branch. Current total equals current 1 plus current 2 plus current 3, and so on. The reciprocal of the total resistance in a parallel circuit is equal to the sum of the reciprocals of the individual resistances. Series parallel circuits combine series and parallel configurations. To analyze these circuits, simplify them by calculating the equivalent resistance of the series and parallel sections separately, then combine these equivalent resistances to find the total resistance. Power calculations are essential in electrical work. Power, measured in watts, is the rate at which electrical energy is transferred. The power formula is power equals voltage x current, or P equals voltage x current. You can also calculate power using the formulas power equals current squared x resistance, or power equals voltage squared / resistance. Understanding single-phase and three-phase power systems is important. Single-phase power involves a single alternating current voltage waveform typically used in residential applications. Three-phase power consists of three alternating current voltage waveforms that are 120 degrees out of phase with each other, commonly used in industrial and commercial settings. Three-phase power systems are more efficient for transmitting large amounts of power. Transformers are used to step up or step down voltage levels. The turns ratio of a transformer determines the voltage transformation. If the number of turns in the primary winding is none and the number of turns in the secondary winding is n2, then the voltage ratio is voltage 1/voltage 2 equals turns 1/turns 2. Inductance is the property of an electrical circuit to oppose changes in current due to the presence of a magnetic field. Inductors store energy in a magnetic field. Capacitance is the property of an electrical circuit to store electrical energy in an electric field. Capacitors oppose changes in voltage. Impedance is the total opposition to current flow in an alternating current circuit, which includes resistance, inductive reactance, and capacitive reactance. Resonance occurs in an alternating current circuit when the inductive reactance and capacitive reactance are equal, resulting in maximum current flow at a specific frequency. When studying wiring methods, it is crucial to understand the different types of conductors and cables used in electrical installations. Conductors are materials that allow electric current to flow easily, typically made of copper or aluminum. Cables consist of one or more insulated conductors bundled together. Common types of conductors include solid conductors, which are single strands of metal, and stranded conductors, which consist of multiple strands twisted together for flexibility. Wire gauge refers to the size of a conductor, with larger gauge numbers indicating smaller conductors. The American wire gauge, or AUG, system is commonly used in the United States. Common types of cables include non-metallic, or NM, cable, also known as Romex, which is used for interior wiring in dry locations. Underground feeder, or ALF cable, is designed for direct burial in the ground. Metal-clad, or MC cable, provides additional protection with a metal sheath. Electrical metallic tubing, or EMT, is a thin-walled metal conduit used for protecting conductors. Rigid metal conduit, or RMC, is a thick-walled metal conduit used in harsh environments. Liquid-type flexible metal conduit, or LFMC, is a flexible conduit that provides protection against moisture. Proper wiring techniques are essential for safe and reliable electrical installations. When making connections, use approved connectors and terminals. Ensure that connections are tight and secure to prevent loose connections, which can cause overheating and fires. Splices should be made in accessible locations, such as junction boxes, and should be properly insulated. When pulling wires through conduit, use a lubricant to reduce friction and prevent damage to the insulation. Follow the National Electrical Code (NEC) guidelines for wire fill, which specifies the maximum number of conductors allowed in a conduit based on the conduit size and conductor size. Grounding is a critical safety measure to protect against electrical shock. Grounding provides a low-resistance path for fault current to flow back to the source, tripping a circuit breaker or fuse and energizing the circuit. Grounding electrode conductor GIC connects the grounding electrode to the electrical system. Common grounding electrodes include ground rods, metal water pipes, and concrete-encased electrodes, also known as UFRs. Equipment grounding conductors, or EGs, connect the non-current carrying metal parts of electrical equipment to the grounding system. Bonding ensures that all metal parts are electrically connected to create a low impedance path for fault current. Bonding is required for metal conduits, enclosures, and equipment. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. Circuit breakers are resettable devices that trip open when the current exceeds the rated value. Fuses are one-time use devices that melt and open the circuit when the current exceeds the rated value. The National Electrical Code (NEC) specifies the requirements for overcurrent protection based on the conductor size and the type of load. Arc fault circuit interrupters, or SIs, are designed to detect arc faults, which are dangerous electrical arcs that can cause fires. SIs are required in many residential circuits, such as bedroom circuits. Ground fault circuit interrupters, or GFCIs, are designed to protect against ground faults, which occur when current leaks to ground. GFCIs are required in wet locations, such as bathrooms, kitchens, and outdoor areas. Surge protection devices, or SPDs, protect electrical equipment from voltage surges caused by lightning or other electrical disturbances. SPD divert the surge current to ground, preventing damage to sensitive electronic equipment. When studying electrical safety, always follow safe work practices to prevent electrical shock and injuries. To energize circuits before working on them by turning off the circuit breaker or removing the fuse. Use lockout/tagout procedures to ensure that the circuit remains energized while you are working on it. Wear appropriate personal protective equipment, PPE, such as insulated gloves, safety glasses, and arc-rated clothing. Use insulated tools when working on only energized circuits. Maintain a safe working distance from energized parts. Never work alone on electrical equipment. Be aware of the hazards of working in wet locations. Use ground fault circuit interrupters, GFCIs, to protect against electrical shock. Follow the National Electrical Code (NEC) guidelines for safe electrical installations. The National Electrical Code NEC is a comprehensive set of standards for safe electrical installations. The NEC is updated every 3 years, so it is important to use the latest edition. The NEC covers a wide range of topics, including wiring methods, grounding, overcurrent protection, and equipment installation. Familiarize yourself with the NEC articles that are relevant to your work. Understand how to use the NEC tables and examples to apply the code requirements correctly. Pay attention to the NEC definitions as they provide important clarifications of the code language. The NEC is organized into chapters, articles, and sections. Chapter 1 covers general requirement. Chapter 2 covers wiring methods and materials. The NEC Article 210 covers branch circuits. This article provides requirements for the installation of branch circuits, including the types of conductors, overcurrent protection, and grounding. For example, Section 210.12 covers arc fault circuit interrupter protection, which requires a size to be installed in dwelling units to protect branch circuits that supply bedrooms, living rooms, and other areas. The NEC Article 220 covers branch circuit, feeder, and service calculations. This article provides methods for calculating the load on branch circuits, feeders, and services to ensure that the electrical system is properly sized. For example, Section 220.12 covers general lighting loads, which specifies the minimum lighting load for different types of occupancies. The NEC Article 250 covers grounding and bonding. This article provides requirements for grounding and bonding electrical systems to protect against electrical shock and fire hazards. For example, Section 250.50 covers grounding electrode systems, which specifies the types of grounding electrodes that are permitted and the requirements for installing them. The NEC Article 300 covers general requirements for wiring methods and materials. This article provides general requirements for the installation of wiring methods and materials, including the types of conductors, cables, and raceways that are permitted. For example, Section 300.11 covers securing and supporting wiring, which requires wiring to be properly secured and supported to prevent damage. The NEC Article 310 covers conductors for general wiring. This article provides requirements for conductors used in general wiring, including the types of insulation, ampacity, and installation requirements. For example, Table 310.15b16 provides the allowable ampacities of insulated conductors rated up to 600 volts, which is used to determine the appropriate conductor size for a given load. The NEC Article 400 covers flexible cords and cables. This article provides requirements for flexible cords and cables, including the types of insulation, ampacity, and uses permitted. For example, Section 400.7 covers uses permitted for flexible cords and cables, which specifies the types of applications where flexible cords and cables are allowed to be used. The NEC Article 430 covers motors, motor circuits, and controllers. This article provides requirements for motors, motor circuits, and controllers, including the types of overcurrent protection, disconnecting means, and control equipment that are required. For example, Section 430.52 covers motor overcurrent protection, which specifies the type and size of overcurrent protection required for motors. The NEC Article 440 covers air conditioning and refrigerating equipment. This article provides requirements for air conditioning and refrigerating equipment, including the types of disconnecting means, overcurrent protection, and control equipment that are required. For example, Section 440.12 covers disconnecting means, which specifies the requirements for disconnecting means for air conditioning and refrigerating equipment. The NEC Article 500 covers hazardous locations. This article provides requirements for electrical equipment and wiring in hazardous locations, which are areas where flammable gases, vapors, or dust may be present. For example, Section 500.8 covers equipment markings, which specifies the markings required for equipment installed in hazardous locations. Joining trade organizations like the National Electrical Contractors Association, NECA, can provide networking opportunities and access to resources. Attending industry conferences and seminars helps stay updated on codes and best practices. After obtaining the contractor's license, consider taking the Master Electrician exam for additional recognition and opportunities. Remember to always prioritize safety and adhere to the latest edition of the National Electrical Code (NEC) when performing electrical work. Good luck with your electrical contractor certification.